Welcome to Math 20-3 Trigonometry Review. Here we're looking at a few questions where you're going to have to solve a few different lengths using some different techniques, as well as some application questions. Let's begin now. So we're going to start by solving for x. I think I set up everything so it's always solving for x. Here it is. Okay. We have the luxury of saying, I can see there's a little bit of a square. A square indicates that we have a right angle. And as such, if we see that right angle, we can assume that Pythagoras' theorem holds true. And that being that the a squared plus b squared equals c squared. Now, what does that mean? Let's just quickly draw a triangle off to the side to indicate why do we mean that that's true, okay? Just before we answer that question, let's bring in a triangle that we can grab. That's a right triangle. There we go. Let's grab this no filler. All right, here we go. We can even stretch it this way if we want. Now, the idea is that if we were to draw a, presumably that's a square there, that we can compose the idea. Again, this was explained in a different lesson, but it's a good review. There's a square. Here's a square. Okay, so whatever this length is here, same as this one, we can consider the area A by A, or area squared. Okay, the space it takes up for this value here. Now if you think of this value as b, and that we make this a perfect square, that means this length is b, and the area, length times width, or b times b, b, is equal to b squared. And so here we have the area of b squared. Pythagoras said that if we take those two squares and they form a right angle to each other, I know it's out of the screen, that we can get the sum of those two areas. They add up to this length, 1, 2, 3, c, a square of c by c length. So the area up here is c times c, which is c squared. So what Pythagoras said was that this area here, which is b squared, plus the a squared, all equals the c area space. Okay? And we can use the idea that we can figure out the side lengths separately from square rooting the area idea to find out the side length of the triangle that they sit upon in a right angle. Okay, so let's go back to our question. So here, it's kind of drawn ugly, but that's okay. It's turned sideways where we see a right angle. We have two of those sides, and they're sitting at a right angle to each other. So we can kind of think of this like, and I'm going to draw this first one and this one only, that we have a square. In fact, it's a little bit messy, so I'll get rid of some of that. Draw a nice little square here. Okay, it's 8.5. And there's another square here. It's not a perfect square drawing, but whatever. It's just a representation. Okay, and I'm going to start writing now that if this is 19.5 and this is 19.5, we can calculate the area. And if this is 8.5 here, that means this is also 8.5 here. And we can figure out the area. Okay, so to do that, we would want to use the area formula, length times width, and I'm going to bring up my handy little calculator here. Whoops, I forgot to make it always on top. So we have area 1. I'll take the bigger one of the 19.5. I'll square that, which is 380.25. So that was going to be 380.25. That's this whole space here. And then the other one, I'll clear all that one off, is 8.5 times 8.5. Gives us a 72.25. So that area there, and that means centimeters squared, both for those. So that area plus that area, we're going to take those sum and add them together. So I currently have 72.25 on my calculator, so I'll add up the other one of 380 plus 380.25. And that is the sum of the large square that should be sitting here. So the area, if it's c squared, is going to be 452.5 centimeters squared. That's what we've done in adding these two sums. Now we want to figure out the side length of this x, which is the result of this area being a perfect square, so we can square root this value to figure out what x is. And on my calculator, I hit the square root button, and hopefully it works. Yes, it does. So I can just hit the calculator and say, okay, well that x value happens to be the square root of 452.5. So x, whoa, that was a little bit ugly. I don't know why. X, and I'm going to just use the approximate symbol because it's not exactly that, because it's not, it keeps going on. And I'll round to 1 decimal place because that's the precision given in the question here of 1 decimal place. So 21, and the calculator 0.27, so it rounds up to about 21.3, and the unit itself should be a length of centimeters. Okay. Now that's solving for the bigger side. All right, clear that, and I'm going to erase my annotations here. Bam. All right, we'll move over to this one here. I think, let me just double check to see that these are all Pythagorean. That was the only one that had Pythagorean theorem using solving for the side length. Let me just double check that. Yes. Okay. So I'm just going to move this calculator so it's a little less distracting on the screen. All right. So now we have ones we're solving for a length, but we're not given two lengths of a right triangle, but an angle. Okay. In order to do this, we need to look at and find a referent angle, which is provided for us. And sometimes it's nice to draw an arc indicating that's the referent angle. And I'd say that there is the symbol for referent angle theta. And you have to identify the parts of the triangle. Okay. Now between the referent and the square, or the right angle, is always the adjacent. So there's the adjacent, and the other length of x happens to be the opposite. Okay, so we have the idea we have an opposite and an adjacent and a referent angle. So we look at our formula sheet to figure out what trigonometric ratio relates these two. If you take a look at your formula sheet, the opposite and the adjacent are related through the tangent. So I would say the tangent of an angle from our formula sheet, and I deliberately said over 1 because this helps us do proportional reasoning, is equal to opposite divided by the adjacent. Okay, so what do we do with that? We have to fill in our values. So I'm going to first start off with taking the tangent of the angle. So that's going to look like tangent of 62 degrees over 1 is equal to opposite, which is x, and the adjacent is 9.8. Okay, this number, tangent of 62, still is not very useful to us, except if it's a number. So we can either use our table or our calculator to figure out what is that tangent of 62, and I told students to be about to a precision of 4 decimal places. I believe with this calculator, this is the first time using these ones, I believe you put the angle in first, so 62, and then you take the tangent. So you click on tangent. And lo and behold, yep, that's the way these ones work. That's about 1.88. Please note that it does say DEG, and it's really tiny script on your, if you're watching the video, DEG are degrees, so that's the degree we're working with. So tangent of 62 is approximately 1.88 .880 and 7 over 1 is equal to x over 9.8. It's going to scroll up a little bit to my arrows here. Okay, now that we have this set up, we have the tangent of 62 is 1.88 over 1 equals x over 9.8. Now, my recommendation is to use proportional reasoning to figure out how do you solve it from here. Well, the simple question is, you go across, what numbers do you have that have 2 working together? 1 to 9.8. Well, that logic is times 9.8 to get from left to right. So I can apply that same logic of timesing that number times 9.8. Now you can use the 4 decimal precision and then times that by 0.98. I currently have it in my calculator, so I'm going to leave it there, which is really convenient for me. Won't change the answer big time in the end. I have it there. I can just go times 9.8 and then hit enter. If it wouldn't glitch out on me. All right. And so here, that approximately is x is approximately 18. And again, I only have 1 decimal place precision from the question, so I typically always put 1, so 0.4. And the units given here this time are meters. Moving along. I'll leave this guy and I'll clear that guy off. Okay. All right, so moving on to this third one here, we have an x in the bottom here. This time our referent angle visibly is 78, and it looks like the x is sitting between the referent angle and the square, so the x this time is the adjacent. And the largest side, which is technically when it's opposed or opposite the square or the right angle, is the hypotenuse. So the idea first, you always got to identify the sides of the triangle. This one's hypotenuse, this is the adjacent, and we have an angle. So working with that, we ask the question, well, what relates the hypotenuse to the adjacent? How are they related? You go look at your formula sheet and you see, well, what trig ratio, in fact, relates the two? If you check that out, this time it is the cosine of an angle, and I always put them over 1 for this purpose of solving for side lengths, is the relationship of the adjacent over the hypotenuse. All right, so we're going to substitute our value for cosine of the angle, so it's 78. I keep over the 1. The adjacent is x, and the hypotenuse is 25.9. Again, this cos 78 is not very useful to us the way it is, so we want to put that into a decimal with about 4 places of precision. Again, with a calculator, you type in 78 and you hit cosine. So it is approximately 0.2079, that's good enough, over 1 equals x over 25.9. Here we have our proportion again. Well, how do you go from 1 to 25.9? Times 25.9. So therefore times 25.9 is the logic. Now I've got my calculator screen, so I'm just going to take my calculator value here without rounding. It's better to do that. Times 25.9. And so it says that x is approximately equal to, and I'll just use the approximate symbol if I can even, to 1 decimal place precision, 5, and 3 rounds up because of the 8 beside it, so 5.4, and the unit is meters. Alrighty, I'm going to move over here, and I'm just going to do a little bit of erasing, just so it's less distracting. You can look back and keep the pacing at your own if you want to pause and see what's going on. Okay, green, I have an angle given. Okay, there's my referent angle. Between this right angle and the referent, there's nothing there, so I'm not going to bother about it. The opposite of the square is the hypotenuse. That's given. And the other side, that is opposite, the referent angle, is called the opposite. So working with your formula sheet, say, well, what relates the opposite and the hypotenuse? Well, the relationship between those two is found in the sine relationship. Over 1 equals opposite over hypotenuse. This time the angle is given, so again, or as it was before, so we say sine of 48 over 1 equals the opposite. This time is 14.3. And we don't know the hypotenuse this time. Ooh, it's changed up. Again, this isn't really useful to us, so we need a decimal, or at least the number value that it's approximately. So we type out the number. Let me clear my screen. 48. And then take the sine, which is about 0.7431. 0.7431. And that's enough precision we need. Over 1 equals 14.3 over x. Okay, so we're trying to go from 1 to x. We don't know what it is. Uh-oh. And logically, this is where it becomes tricky. Like, how do you go from 0.7 to 14.3? Or what do you got to multiply to get from 0.7 to 14.3? Well, if you don't know, we remember the trick is to take the final digit and divide it by the first digit to figure out the multiplier. So I'm going to clear my screen because I can. 14.3 divided by the 0.7431, that's fine precision, that says if we multiply that by 19.2, so back to this one, so 19.243, etc., 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 we'll get exactly 14.3. So 1 times that 19.243708 and all that kind of stuff, it will give us x. Well, wait a minute. 1 times that number is just that number. And so therefore x is about 19.2 and doesn't round up. So, and the units are centimeters. That was fairly quickly going over 4 questions of utilizing the angles to solve side lengths. We're now going to go and utilizing a couple sides of a triangle to solve unknown angles. And we're going to go back down over here. Okay, I'm going to leave these calculator up here. So this time, we're given 2 sides of a triangle. And it's very important also, I know it's hard to see here because I was trying to utilize this technology on here. There is in fact a square, although you may or may not see it on the video resolution. There is a square indicating it's a right angle, so we can use right angle trigonometry to solve this. Here, lo and behold, is a referent angle. And here is a right angle, by the way, just wanted to say. Well, there's nothing here between the referent and the right angle, so that's the adjacent. Nothing there, not useful. Over here, I could also look at the opposite. We are given the opposite, and make a little arrow here. This guy points to the hypotenuse, the biggest side. So we have the opposite and we have the hypotenuse. So we need to work with a trig function that relates the two, opposite and hypotenuse. Conveniently, we just did one that said that opposite and hypotenuse are related by using the sine of an angle. Opposite over hypotenuse. Okay, let's see what we got. Sine of theta. Well, we don't know what sine of theta is, so we leave that as is. Over 1. And we just leave that over 1 because we have no idea what we need to work with that. Opposite is 12. And they're in the same unit, so I can just simply put the proportions over 16. Now, because we're trying to find an angle here, we don't really need the over 1 thing. We don't necessarily need it, because I typically choose to use the side length 1 over 1 when I need proportional reasoning going back and forth. So we have the sine of an angle is 12 over 16. Now, those are not very useful in and of themselves, but if we put as a decimal, because we tend to seem to get those decimals, 12 divided by 16 is about 0.75. And I picked numbers that were nice and easy. Later on, they're going to be not so friendly, but whatever, 0.75. And for those of you who like to use the chart on the, because I've given you the tables, you put 0, 0. And you can use the table to find out which is the closest sign that has the closest decimal to 0.7500. You can do that now. Or what we can use as the calculator is we're trying to find the angle by itself. So what we do is we take the inverse of the trig function we're working with. This is called the inverse of 0.7500. So, how do we do this? Well, we have our 0.75. That's what these calculators work with. You have to put what's inside the brackets first, and then say we're trying to find the angle. Now, as opposed to just doing sine, we need to use the inverse, which is that little yellow sine to the -1. So we go second function, sine. And this is what tells us the approximate angle is. And again, you'll see that it pretty much corresponds to what you see on that chart with the integer values, that the angle is approximately 48.59. Or if you were looking at your table, rounding to the nearest whole number, it's about 49 degrees. That will be the closest value you should approximately find that's closest to the 0.7500. All right, let's try a few more that uses the different trig ratios. I've got another one here that I deliberately just played with some numbers randomly and said, let's see what we got. Okay. Again, you really can't see it, so I'll highlight it this way. Probably should have just done this in the first place. Whatever. There is, in fact, a right angle, and so therefore we can treat this with the proper trigonometry that we've been studying so far. The referent angle is x. Here it is. And we call, oops, I'm still in the straight line mode. We call that a theta. Okay. Now, here's the referent angle. Between the right angle and the referent angle, we can see that there is something, and that's the adjacent. And the right angle always points to the hypotenuse. We'll ask ourselves, what relates the adjacent and the hypotenuse? You look at your formula sheet, and I'll go back to blue. That we remember that cosine of an angle is equal to the adjacent over hypotenuse. And I believe I always put over 1, but I'm trying to solve for the angle. I don't really need the over 1 proportions. Okay? So we don't know what cosine of theta is, but we do know what the values of adjacent hypotenuse are, and that it's going to be 6.2 over 13.5. Now the centimeter over centimeter reduces. We don't bother with that. It's just the ratio itself. So we're going to say cosine of theta is approximately. Now here, because I just play with numbers, I don't know what it's going to be. So I'm going to go 6.2 divided by 13.5. Ooh, and it's got a funny bar. My calculator does a little funny bar. So it's going to be 0.4592. And really, even though that portion repeats, is what the bars tell us, that's as far as I really need to do. We need to figure out the angle, so you can look at your chart and find out which cosine under the table is closest to 0.4592. Or you can use the calculator, using the second function cosine of 0.4592. Now, because on my calculator, all I have to do is press the second function and apply the cosine feature to it. Indicating, obviously my diagram's not greatly to scale, that the angle is about 62.6, or rounding up to about 63 degrees. Okay. Moving over. Ooh, the x is placed in a different location this time. Again, by the way, there is a little square there, and so this is a right angle. Here's our referent, so that's our theta, our unknown value of angle. Between the referent and the square, we have the adjacent. Now this time, as it appears, we've got the opposite. And the relationship between the adjacent and the opposite is, in fact, the tangent. So the tangent of an angle is the adjacent. Whoops, I made a mistake. Let's just undo that. Okay. Opposite divided by the adjacent. Should always check your formula sheet just in case if you're not quite sure. I don't have one in front of me. I was going by memory, and sometimes I forget. Opposite is 11.4. The adjacent was 7.2. That equals the tangent of an angle. Okay? So the tangent of the angle, I'm going to get the approximate decimal using the calculator, which is totally fine. 11.4 divided by 7.2. 2. Oh, it's about 1.583. So 1.583. And it says that that 3 happens to be repeated, so I can even add the extra 3 if I want to. But because I'm going to use a calculator, all the decimals are all there. Want to find the angle by itself. So we have to undo the tangent function by using second tangent of 1.5833, just in case you lost it on your calculator. Mine's on my screen, so I go second function of tangent and apply that to that number. So it suggests to me the angle that I've drawn here of x is about 57.7 degrees, or roughly 58 degrees. Pretty sure that's all 4. Yep. So there's 8 different possible scenarios, or 7 rather, scenarios of solving for side lengths and solving for angles. What I'm going to do now is another set of examples that are going to be ones of problems that involve more challenging two triangles. I'm going to stop this video and put it on a second input, okay?